Simon is the Director of the Decision Sciences Programme at CSIRO Data 61. Simon has been the leader and principal investigator in numerous research project teams looking at supply chain logistics, service delivery systems, infrastructure and national hazards during research and development career spanning almost 2 decades. He is an operations research practitioner with a record of publications at international conferences and in academic and industry journals. And over the past 10 years, he has delivered many talks, seminars and short courses to industry and data science, logistics, warehousing, distribution and infrastructure planning. He is the Victorian and immediate past president of the Australian Society of Operations Research and has been on the National Committee member for the National Logistics of Australia. So please welcome our final speaker tonight, Simon.
Thanks, Kyle. That bit's always the embarrassing bit, you know, the whole bio thing. So I run Data 61 in Victoria, as well as one of the 4 research programs. Data 61 is CSIRO's data arm, data and digital arm. And it's formed from NICTA, which was an organisation that existed for about 15 years, and CSIRO's divisions in maths, stats and ICT, and that's about 3 years ago. CSIRO does sheep and plants and animals and all that stuff, and some people got their head around we do data and digital things. And we make technology and we do sort of consulting-y style of work and on bleeding edge things. But I want to reframe that a little bit, particularly in this context. Data 61 exists and CSIRO exists to help industry, all right? And take technology and apply it to solve problems and help industry do that. One of the ways we do that, and the new way we might enter into, is nurturing other people's data science capability. So allowing people to do their projects and build their stuff within our walls with our help. So keep that in mind when it looks like I might be saying, well, look how good we are, you know, just admire us and maybe buy stuff from us, when actually one of the ways, particularly in Victoria, we're positioning is to help your people upskill and apply it back in your businesses. Now in AI, and we've already heard AI is, no one agrees on a definition, what is it or what can it be or whatever else. And the more, the AI definitions that seem to stick actually talk about the characteristics. If you're a person who you observed AI, what does it look and feel like? It can talk back to you, it can make some decisions, it can interpret what you say, etc., those sorts of things. Now, in a broad definition of AI, lots of Data 61 do some kind of AI. Computer vision stuff, language processing stuff, sensing, IoT, edge computing, looking at materials and processing experimentation and fusing modelling and data together. Interesting computer vision, Doreen showed the bagels and the puppies. One place where we use it is in sports, so elite sports, in diving in particular. And it's interesting where AI algorithms train to recognise people and are very good at it. When the people are tumbling and upside down, how hilarious AI's results are in that kind of context. So that leads us to what's this model-driven qualifier I've got here. We use both, well, essentially we say is model-driven, where you actually understand a fair bit about the world. And you're using learning techniques or data techniques to feed into a model and parameterize, understand the parameters in the model and go forward. And then there's learning type approaches to AI, which is where you don't put in structural information. A lot of what I'll talk about here is that model-driven kind. So we can construct a picture of the world by using our intelligence and use AI techniques to use and populate that. So, I'm going to start with a story. Once upon a time, not too long ago, some relatively smart and relatively experienced people decided they'd build an operations management system for a steel facility. And they more or less knew what they were doing. And the basis of this facility was you've got steel coils, big heavy things, being produced, and they'll step through either direct to a berthside warehouse and then onto a vessel, or they might go through multiple steps, and the multiple steps are more expensive. You don't want to do it. But this supply chain, this internal logistics system, faces a lot of surge So one week you might do 100,000 tonnes of steel, the next week you'll do not many. That's driven by the vessels that turn up. Lots of data in the system, and the organisation that we were working with and within had many, many systems and had done quite a lot of work to get their data into a spot where you could query it with APIs and stuff. But this is pre-GFC, so it's a decade ago. And so one of the core things about this system was that there are bays in this warehouse, this very preferred warehouse next to the berth. We really want stuff to go straight from the mill to this warehouse because we only handle it once. When we say double handling, we're not going to drop the coil, there's not damage, sort of stuff that may happen, all sorts of reasons why we'd like to go straight to this warehouse. And the way it works is you reserve some bays for the coils that are intended for a particular vessel and are a particular specification. And the core of the sort of system says assign a bay, put stuff in it, and then once the vessel's turned up, progressively put each piece of the manifest onto the vessel, and you've got lots of choices. Which bays do you go for first? Which part of the vessel? Which vessels do you do? And that ordering matters because you might want to clear space in this warehouse because there's new stuff being produced. If I clear this bay, I can put new stuff in. If this bay is very big, I'm not going to clear it in time to get my next lot of coils, so I might go for a little bay. Okay, so far so good. We seem to be able to get most of this data. We can build scheduling systems that seem to be able to do a good job. We start to wire this thing up. And see, some of these bays have got quite a lot of coils in them. And then we find out one day in Wollongong, so that tells you who this was for, we don't have any way of knowing at a point in time how many of the coils are in the bay and how many are on the boat. We only know this at midnight every day when a meatware sensor enters some information. $200,000 worth of development down the track, nothing like this is the end at that time, around about that kind of figure. Killed by one piece of data, or one style of data, and we had everything else. We knew everything about the coils, we knew the quarantine times, we knew the vessels, knew all sorts of things, but the danger of data, do we have 100% of the data that matters? And the story here is going to be about how can we use sensing and AI to fill that gap which has killed more projects than anything else in this kind of space, and it actually kills most projects that I've ever seen around this kind of area. So often as well on top of this, but this is more an aside, there's usually little or no data about capacities and capabilities of your system. You think about the systems you might run. You might know the orders, you might know a whole lot of things about the products. Where's the data about how many things something can carry? Or who's qualified to do what? Or what's the uptime of a machine and how many hours of downtime per uptime hour do you need to maintain it for? That's often missing. So yeah, missing inaccurate and frequently updated data will kill projects, does kill projects, kills more projects than anything else. You've got this other thing, even if the data's kind of there, are there random gaps and mistakes in the data? And this is one of the AI uses. Can you use it to find these mistakes? Because if I have 99 times out of 100, maybe I can know what's in that bay of coil. But if I've got it wrong 1% of the time, that schedule is stupid. And particularly, again, your meatware sensors have got a fairly poor tolerance of these systems telling them what to do. That's enough to also kill your project down the track. So using AI to fill the gaps is also a big deal. All right, so this is the big question. Can we reach back along the data pipeline? Rather than be in the enterprise systems, rather than be in the office, rather than just worry about where's that data gone? All right, we go back to we've actually got to get into the acquisition game, the sensing game. Can we reach back along that data pipeline, use sensing and AI to overcome these data issues? And that's really the point of this talk. And yeah, you can. And I'll show an example where we're doing this. So just as much as anything, some definitions. So IoT, again, people can mean it to mean different things. Let's just say low cost sensing. Sensing is very cheap and gets cheaper. And if you have companies, and this does happen, major manufacturers who actually allow their staff to start installing Arduinos and Raspberry Pi stuff all through the factory to muck around with this stuff. And you don't use that for production necessarily, but these costs are going right down. That gives us the ability to monitor and measure facilities at all sorts of scales in a way that wasn't really available 10 years ago particularly. You could do bits of it, but now it's cheap, now it's much more accessible. And AI in this context is where you use learning and model-driven stuff together to take this data and make sense of it. I might know the position of a tool or a tractor or something like that, but I need to make that make sense in the context of a schedule or the activities I'm trying to do. Just knowing that pallet 6 just passed the end of Mark's chair there is not a useful fact for managing anything yet. So a key thing, as well as the sensing where we use the AI for, is how do I step that up to this is a piece of knowledge about the tasks I'm trying to do. And that's where the model-driven AI comes in. So there's an example that we're involved in with an aircraft manufacturer. And there are position sensors mounted to jigs and fixtures that carry around pieces of a large passenger aircraft. The situation here is, as you can see, this is a fairly to scale picture of the factory floor. Lots of room for congestion here. It's not two words you should put together. Lots of scope for congestion in this relatively small room where there is only one door to get in and out of here. And sometimes, this is in northern United States, it's windy and snowy out there, you can't open the door. Sometimes they're towing a US Air Force 767 base tanker out the side and everything must stop. So you've got a single resource and you've also got work that's highly variable, as well as all sorts of things about people needing to be FAA certified to work on different jobs. So lots of complicated things. We need to turn these position sensors into information on when are we going to finish these jobs? Because I need to move stuff around. Am I going to move the first thing or the second thing first? How am I going to shuffle? How can I respond with this schedule without having to think about it? Right, use intelligence in this to not have to ever have a conflict because the system's watching, looking at these signals, adjusting in time. And this is a real system. This isn't imagined. So the real system's been put in, this has been done, but I'm going to turn this story around too. You have to be pragmatic. So this here is actually the same map of that system I was talking about. And this actually feeds into Doreen's point about reinforcement and learning. Where's reinforcement come from? And so one of the things about deploying this stuff is we had to deploy meatware sensors as well as RFID location sensors. We wanted to deploy acoustic sensors so we knew when people were doing drilling jobs and relate that to what part of the assembly you're on, and couldn't quite do that just from union issues and other things. But what we did need to do is actually put in a visual representation of that plant as well. So when we haven't detected the job coming in to, say, cell 6 or 7, we can dispatch someone to understand what's happening, because did the RFID fail? Is the thing really not there? What's the reason it's not there, or what's the reason it's still there? And that's an important part too. It's not just the events you detect, it's the events that haven't happened that you need to know about. And so you can't just watch signals, you've got to actually watch for non-signal as well. So one of the key things about this whole IoT-enabled system was building a tablet-based interface where people were providing that reinforcement to the system. The other thing that was important, and I think you'll be able to relate to this, is showing off. So this is one part of what clearly is Boeing in the US. I didn't leave too many hints there. Many different production lines there. The one that are our friends, they We're seeing our 3D projections of the plant, which is how you get a visual cue of is the system keeping up. But they also saw if they showed that on their control room, that was much better than the Gantt chart for the next line down the corridor. Final slide. This is a real space. I was having a conversation just before with someone who's doing basically the same thing in construction. So deploying sensing, putting logic over the top, learning AI and model-driven IA to do these things. It's not tomorrow, it's now. But this is a winery in New Zealand 12 years ago. That's actually a very good system that they use, and there's all sorts of things going on there. So this stuff is not easy to, when you look at a manual system that's working well, how do I introduce AI into this? How do I go about doing this thing? And this is really the point where we think, and again the conversation I had earlier today that's important. Something like Industry 4.0, we often get told that go and buy all this kit, because everyone else is, and stream your data to the cloud and draw some graphs and do these things, and it's a good idea. It's the trend, so go and do it. Whereas what a lot of us are finding is really, if you're going to actually do this adoption, you've got to start with the reason you're doing this. Don't start with the sensors. Don't start with putting RFID out there. Start with what's the problem you're trying to solve. Then deploy what you need, not the other way around and deploy and have a whole lot of data, more data than you don't use. So in this winery, what would we do first? I couldn't quite figure out what they'd do first here, but one of them is just understanding where is everything in the landscape. Because when stuff starts to happen in a winery, when say rain events come in, they have to reorganize what's basically a whole sequence of harvest operations that go into one fermenter. So understanding where everything is a major part of this, and that's where you might start there. So how do I instrument up my trucks? And I've seen this happen in Echuca. There's a tomato company up there who decided that one of the things they must do is know where the trucks are, and that's really important for their production. That is the end, I think. Yes, it is, so thank you.